So this time we have a different Mips question, and it says the Mip instruction, which is store word $9, comma minus 2 into bracket $29. So this is a store word instruction, and it's trying to store a word from register 9, and the base address is located in register 29, and we will offset it by minus 12. So we'll go 12 backwards from the address, right? So maybe if 29 pointed to address 16, then we'll go 12 backwards. So we'll come and store it at address 4, okay? Something like that. It's executed on a single cycle data path as shown in the figure. So that's the single cycle data path you see. It's not any different from the Mips you've seen so far. Assume all the registers are preloaded with the register number prior to the execution. Okay, this means that all the registers initially, right, they have their register number stored in them. So register 1 will have 1 stored in it, register 2 will have 1 and 2 stored in it, right? So it means that register 20 now have 29 stored in it. Okay, prior to execution, and each data memory byte is loaded with the least significant byte of its own address. For example, 0x, a lot of zeros and ones will contain 0x01, 0x lot of 0 and 2 contain 0x02, and 0x3f will contain 3f. So what this means is that so this is hexadecimal, right? So when they say the least significant byte, right? A byte is 8 bits, right? And in hexadecimal, each number is 4 bits, right? So it means that address 0x00001 will contain 0x01 because it contains what? That's the last two, and that's the last byte of its address number. So is the for the 0x0002. Right now, this is just initialization, right? I think you use it in solving the question, so they are just initialization. So for example, this instance will contain 3f because of the last byte is what? 0x3f. Thus, if you load a word from 0x03020100, you will get this one, right? And if you load a word from 0x0b08908, you get this one. So this is just emphasizing the first point, right? Telling you that anytime anytime you load a word, um because of how we have initialized everything, you get the last byte, right? And the byte I said is just the last two numbers, right? So for example, here when you load from this address, right, because the last byte is what? 0x08, the data you fetch will contain what? 0x0008, right? Then note that little endian is used. Copy buses and control signals on the next page and fill in their values. You must place X in the blank if the signal is a don't care. Alright, so let's start solving the question. Now, this is the data part they give you, right? So it's nothing different from the mixed data part. You have everything here, and they also show you the storage instruction, the instruction format, as you can see at the top. So let's start solving the question. And the first part, it says what you have to fill instruction 15 down to 0, right? 15 to 0, assign extension. Now, if you know the store word instruction format, you realize that 15 to 0, right, is where the offset will be stored. Now, what is the offset? The offset here is what? Minus 12, right? So that's the store word instruction. The store word instruction, the number we specify along with the base register address is the offset, right? So the number we specify along with the base register address is the offset, right? Now we are looking to see its value after sign extension here, right? So it's quite easy. First, let's write minus 12 in binary, and I hope you are now conversant with conversing from positive to negative. So minus 12 in binary will look like this. And even if you're not conversant, I think even your calculators can do this. Yes. So at the end of the day, we are just looking for minus 12 in binary, right? And minus 12 in binary looks something like this, right? As you can see, forget about the sign extension. There are a lot of ones, but it looks something like 10100. That's minus 12 in binary. However, you realize that here they are requiring you for what? They put 0x there. What it means is that they want your answer in hexadecimal, right? And that's the answer in hexadecimal, right? Now this is a 32-bit architecture. So you only have to write 8 of this, the first 8 numbers starting from the what, right? Right. So this is hexadecimal. So you just have to write only this 4 as your answer, right? And now why do you have to do that? Because minus 12 is less than in when you put it in 15 bits. When you put it in 15 bits, you get a number. You get the length less than 32, right? But when you extend it, sign extension means that the first bit you would replicate it with once, right? So minus 12 in binary is just these last 5 numbers, right? Now in 15 bits, it will be the first 15 of this. Now in 32 bits, yes, we just added to the ones in front of to get the 32 bits. That's from previous courses, so it's quite clear on that. So yeah, so this is the answer expected. So you can just copy and paste it. I think let's just paste it here. So yeah, so that's our answer, and our answer is minus 12. And I also had to ensure that what it is a total of 8 separate units, right, in hexadecimal, because in hexadecimal each number is what 4 bits. So 4 times 8 is 32. Yeah, so it's a 32-bit number. Then the next part is um we are asking for read data one, right? So let's go and see for read data one now. Read data one is the one at the top, right? Now, if you remember well in your execution of the store with instruction, you realize that read data one is what will read the base address, right? And the base address is stored in register 29. However, in the question, they told you that all registers are preloaded with their register number prior to execution. So it means that register 29 stores the number 29, right? So you can go through the same procedure again to find the hexadecimal value for 29, right? Which the hexadecimal value for 29, which is just 1D, right? But we need 32 bits, right? So in 32 bits, 1D means we have to start it with 6 zeros. So 1, 2, 3, 4, 5, 6, and 1D, right? Yes, and we are done. So that's the hexadecimal value for 29. And I believe the question would have been best if here was 28 rather, so that the whole thing would be word aligned. But let's forget about it. Let's just do as the question says. And the next part is read data 2, right? Now read data 2 is this one. Remember that in store word, we'll pick the read data 2 directly and go and put it in memory, right? Now the read data 2 is the address which is specified by what? $9. But they said that what is stored in $9 will be 9 because all registers are preloaded what? With their register number prior to execution, right? So it means that $9 stores 9. So it means that we have to find 9 as well in what? 9 as well in binary. So 9 in hexadecimal is still 9. It's less than 15. So it's still 9. So it means that we have to put 7 zeros and the 9, 7, 9. Right. Yes. So that we have this one as the answer. Now, the next part is it said find the right address in data memory. You realize that in this instruction, when you're executing the sign extended number, right? We will take it, we'll add it to the base address, and that will give us the right address, right? So in essence, the right address will just be what? The 29 plus the 12. Remember, $29 stores 29, right? And 29 plus negative 12, right? So 29 plus negative 12 is, I think, 17, right? So it means that what you're expecting is the number 17. And number 17 in hexadecimal. In hexadecimal looks something like this. It looks 1 1, right? Which is just yeah, 2, but we need the total of 8. So you can see 1, 2, 3, 4, 5, 6, 1, right? Then yes, so that will be the right address in data memory, right? So that actually have been 16 if the register address was 28, but it's still okay. Yeah, so that's the right address in data memory. Now, these are the numerical parts. The next part are just the control signals, right? So the control signals, it comes from your knowledge from how the store word instruction works in Mips, right? So the first one is the ALU source. So you go and check which control signal is called ALU source, this one. However, in your execution, remember that we pick the sign extended, right? We pick the sign extended, not the what read data to go into the multiplexer. The read data to went to memory, remember. So we pick the sign extended version, right? And the sign extended version was selected by the ALU source signal. The ALU source signal is what? It will be 0 for read data to and 1 for what? The sign extended version. Now, since we use the sign extended version, means you have to choose one, right? So it means that the ALU source will just be 1. We will set it to 1. Then the next part is we have to look at they say PC source, the program counter source. So we have to go and check the program counter source. Now this is not a branch instruction or how do you call it? Yeah, a branch instruction or a jump instruction. So it means that the program counter will have to just do PC plus. When you check the architecture here, PC plus 4 will come through here, right? Now we have to select 0 to take PC plus 4. Or if you select 1, we'll go and take from the second part, which is for a branch instruction, which you don't want. So you have to take 0 here because this is not a branch or a jump instruction. So it means that the PC source has to be 0. Then the next part is regdist. Now regdist is here, right? As you can see, right? And the regdist is the one which is used to switch between you selecting from um 15 to 11 to write to the register or selecting from I think 20 to 16 to write to the register. Yeah, so now that one was used to differentiate the right location for the load word and the other arrow type instructions, right? However, even store word does not even write to memory at all. So it means that we don't even care what regist is, right? And we can just put X here, don't care here, right? Because store word doesn't even write to memory. Then the next part is okay, let me see the next part. The next part is mem to reg. Mem to reg, I think is at the end here, right? Now we don't write to memory, so we don't care what comes from memory and goes back, right? So we can put a don't care for that one as well, right? So that's a don't care. And the next one is what? Mem write. Where is mem write? Mem write is this signal. And this signal is crucial because remember we are outputting the read data too and we are putting it in memory. So it means that we really need that signal, right? So mem write has to be asserted so that we can store it in memory. Right? So here has to be 1. Now the last part is what? Read write. So let's go and see read write. Well, read write is this signal. And read write is asserted if you want to write to what? The register file. This instruction does not even write to the register file. But we can't go and put a don't care there. If you put a don't care there in the case where it is 1, right, some signal may be just then to be accepted. So you have to make sure that we don't write at all. So you have to be careful. So the difference is that where you are dealing with memory, where it is an enable signal for a read or write, right, you have to be specific to make sure that it is 0 or 1. You can't just treat it as a don't care. But where it is a multiplexer select signal, I mean, you can treat it as a don't care. You don't really care what goes to the multiplexer. So it means that this one, the red right, you have to be careful to make it 0. Yes, and I think with that we have come to the end of the question. So you can just drop any questions or misunderstanding in the comments and we'll tackle it later. Thank you.